All right, welcome to Unit 12. It is the unit from hell. Chuck, Seth, come on. We're starting, and you actually are on tape being scolded. There is proof. I totally ruined your possible political career. I will pull this up on the day you run and say, see, Seth, I know. It's already ruined from other things? Okay. Well, Unit 12 is going to be a conglomeration of everything you've learned thus far, plus like the 5th level of Dante's Inferno. Like, is the 5th the worst or the 1st? There's 5 levels, right? Have y'all not read Dante's Inferno? Oh, okay. Well, anyway, one of the levels that's really bad, like the hell of hell, that's what we're about to approach here. So up until this point, if you look at the board, we can find the pH of the first 3 of these: strong acids, bases, weak acids, bases, and salts. You should be really, really, really solid on those, right? Well, today you're going to learn what a buffer is and learn how to find pH of buffer solutions. That in itself is pretty easy. It's when we mix this all together and do what I call invader problems, where things get kind of crazy. So let's start by talking about what a buffer is. When you say what a buffer is in terms of medicine and things like that, people see a buffer as something that helps stabilize the pH of a system. So if we have a buffer in any sort of, we have a buffer in our blood, for instance. There's lots of different buffers in our bodies that helps maintain pH. So pH is stabilized. Why that is because of what components are make up of a buffer, or make a buffer. The first would be, we can have, what's wrong? We can have a weak acid. Did I misspell stabilized? Probably. Well, just tell me. I'm not too proud. Don't sit there and behind my back say it, and then when I turn around, and so that makes me feel worse. Just tell me. A weak acid and its conjugate base, or you can have a weak base and its conjugate acid. So when you look at a problem, if you see that combination of stuff, you know you have a buffer. So let's give an example of what I mean. If we have a weak acid like C2H3H, C2H3O2, that's acetic acid. Now, what form will we see this conjugate? You'll always see the conjugate in the form of a salt. So what salt would contain the conjugate base to acetic acid? Give me a salt, any salt. Na, sodium acetate. So you see how that's a salt, but when you remove that Na, that is the conjugate to that weak acid. Got it? Okay? So it always has an acid or a base and a salt that contains the conjugate. So if I were to say this is ammonia, give me an example of what a conjugate acid containing salt could be. Yep, perfect, NH4Cl. So this would be an example of a buffer system. Now, why do buffers help stabilize pH? Well, it's pretty simple. For instance, in your blood, I won't use the blood. Let me just use one of these systems. Let's say we have, let's pretend you had acetic acid in your blood, which you don't, but you had that buffer. So let's say I took one of you into my scary lair and injected you with acid. Okay? If I injected you with acid in your bloodstream, that H+ would react with what part of the buffer system above? The conjugate, correct. And what would it make? It would make acetic acid. So who cares? Why is this good? Well, think about what's happening here. A really, really strong acid was put in your blood. And what was it converted to? A weaker acid. So it helps that keep that pH more stable. Is the pH going to go up a little? Yeah, a smidge, but not as much as if this thing were added all by itself. What if I took you to my lair and injected you with a base? What part of the buffer would that react with? The acid. And you would make what? Water and the conjugate base. Okay. So we put in a really, really strong base, but thanks to the buffer system, only a small base is going to, only a weaker base is going to affect things. Okay, so that's what's important about a buffer. It can take a system can take hits from both the acid side and the basic side. So when we talk about finding pH of buffer systems, you can do what we call the common ion effect. Those of you who took pre-AP, you actually did these rice tables where you had two initial concentrations and solve from there. It's totally fine to use a rice table for buffers, but I'm of the opinion that you should use an equation called Henderson-Hasselbalch. There's a lot of people who disagree with me about this, but I find student success much higher using this equation. You don't have to memorize it, but you will just because you're going to use it so much. You'll know it by the end. But what's great about this is it's a simple plug and chug, and you get the answer you need. There are two versions of it, the acidic version and the basic version. The acidic version is pH is equal to, what did P stand for again? It's the old-fashioned way for saying negative log. So pH is equal to pKa. You take the Ka of this acid plus the log of the concentration of the ion over the acid. Now, there are a lot of people who, a lot of teachers who say this is why it's bad. Students forget what to put on top and bottom. It's always the conjugate. It's always the thing that's got a charge that goes on top. So the concentration of the ion divided by the concentration of the acid. Kb, the POH version is the exact same except you use the negative log of the Kb. And it's super simple. These problems are really, really fast to solve. Just point out that notice this does say bracket, so this is a mole per liter concentration requirement. So what I want to do is just jump in to do some simple solving problems. Let's go to number 1. We're going to get back to this tips for solving acid-base shortly. Number 1, calculate the pH of a solution, which is 0.53 molar H, some crazy acid, plus 0.5 molar sodium, that acid. So do you see how one is an acid and one is the salt that contains the conjugate of that acid? And we don't know the name of that acid. It's some crazy organic acid, so it's always going to be weak, right? So we have a weak acid and its conjugate base listed. All right, so I'm going to make up a K. Help me make one up. 4.2, what do I want, times? Okay, no, let's make it much smaller than that. 8. I'm just making it up. That's the K for this acid, we're going to say. Now, since this is an acid and its conjugate, we're going to use the pH version. So I'm just going to write it out. pH is equal to the negative log of the Ka plus the log of the concentration of the ion over the acid. All right, so plug and chug. This is it. Negative log 4.2 times 10 to the negative 8 plus the log. What goes on top? Which one? The ion. Which contains, where's the ion coming from? It's the salt, right? So what's the concentration? 0.5 over 0.53. Plug that into your calculators and solve, and we need 2 sig figs, 2 decimal places in that pH. So we get a pH of 7.35 just by plugging that in the calculator. Now I'm going to do a little side thing here just for those of you out in the world and maybe you guys who don't like the use of Henderson-Hasselbalch. I'm going to show you why I like this. This didn't take any time at all. If you wanted to use a rice table in a problem like this, once you identify that you have a buffer, you would go and take the acid or base, the weak acid or base, put it in a rice table and add it to water. And what do we make? We make C6H4NO2 minus plus what? H3O plus, correct? And then we put our initial concentrations in. Since we have concentrations for both, this is 0.53 and this is 0.50, and we have none of this. This is why it's called the common ion effect, because we have a common ion amongst both of those initial concentrations. Minus X plus X plus X. You already know how to solve all this. You can trump it. But do you see why Henderson-Hasselbalch is just faster? You can trump that, you can trump that, solve for X, products over reactants, set equal to K, find H3O plus, and take the negative log of it. You're going to get the same answer, okay? But again, I prefer Henderson-Hasselbalch. You've identified you have a weak acid in the conjugate, plug it in a Henderson-Hasselbalch and be done with it, okay? All right, let's go do another one. For this next problem, I actually know the Kb for this. The Kb for ammonia, 1.8 times 10 to the negative fifth. All right, so looking at this, they want the pH of a base and its conjugate. Since it's a base and its conjugate, we're going to use the POH version. POH is equal to the pKb plus the log of the concentration of the ion over the base in this case. So POH is equal to negative log 1.8 times 10 to the negative fifth plus the log concentration of the ion. It's this one. Oh, but look, what's the log of 1? 254. So the log of 1 is 0. So we just take the negative log of 1.8 times 10 to the negative fifth, and in doing so, please tell me you get a POH of 4.74, and therefore you get a pH of 9.26. Now, I could say, hey, it's a basic system because we have the base in its conjugate acid, so we should have a basic pH. It's actually something we can't check on like we could with other systems, because if we had a ton of conjugate acid, if this were super, super high concentration of this salt versus a very low concentration of that base, we might have an acidic pH. So you really can't assume just because we use the POH version we should get a basic pH. It's not necessarily going to happen that way. Okay? Do y'all remember the lab we just did? Remember the lab where we said if we had this, and remember you did the lab where you neutralized, you took the acid, you neutralized half of it, so what was equal to what? Wasn't that equal to that? And so you found the pH just by, if you found the pH, you could figure out what Kb was. Another way you could have done this is use Henderson-Hasselbalch, because in the lab situation, you created these two being the same, so you created a log of 1. So I could have also taught it to you this way and say, hey, this is Henderson-Hasselbalch, these two things have the same concentration, therefore your POH is equal to the pKb, which is the exact same thing you did in the lab. Just trying to connect something you just learned to something else. But we didn't do it that way. Instead, we said OH is equal to Kb. Exact same thing, okay? You actually created a buffer system when you were doing the lab. You took half of an acid, converted it to that same amount of conjugate base. All right, and everyone did great on that lab? Nice percent errors? They're small numbers. Your percent errors are going to be high. I'm aware of that. Don't worry about it. Hope you didn't lose sleep over it. Somehow I doubt you did. All right. Let's do a couple more of these. Calculate the pH of a solution prepared by mixing 20 mils of 0.3 molar acetic acid with 20 mils of 0.350 molar sodium acetate. The Ka for acetic acid is equal to 1.8 times 10 to the negative fifth. Okay, how is this one different than the other ones we did? Well, you're given volume, so what does that mean, though? Calculate the molarity after we do what? After we mix them together. If we're mixing them together, what's the word? I'm looking for a word. What are we doing to those? We're diluting, exactly. We're mixing them with double the amount of volume, so technically their molarity is cut in half, right? I mean, it's easy just to divide those concentrations by half, but I'm going to show it with MV just in case. Maybe it won't be half next time, so you know how to do it. So are y'all okay with me writing acetic acid as that? And then the acetate ion as that? Okay, so our acetic acid, if we want to find its new concentration after the dilution, we're mixing 20 mils of 0.3 molar to make a total of 40 mils of what molar? Question mark. So that comes out to be 0.15 molar. of that. And then the acetate, we have 20 mils of 0.35 molar. And we're making a total of 40 mils of what molarity? 0.175 molar. So those are our two molarities. So what version of Henderson-Hasselbalch do you want to use? Because I definitely have a system here that's a buffer. Which version? The pH version. pH is equal to the negative log of 1.8 times 10 to the negative fifth plus the log, what goes on top? The ion divided by the molarity of the acid. So much faster than rice tables. Come on, that's crazy fast. We want, everything has 3 sig figs except our K, so go ahead and give me a 2 decimal place pH. 4.81 is correct. Okay? All right, so now we're going to work a little bit backwards here. They want to know, specify the reagents and specific concentrations of each reagent needed to prepare a buffer solution which would have a pH of 4.19. Your best buffers are chosen in an area that the acid or base is near that pH. So I'm going to stick with an acidic system here, and just for ease, we're going to choose acetic acid and sodium acetate. Okay? That's the buffer system we're going to use here. I need to know what concentrations of these do I need to make a pH of 4.19. So how should I proceed? Start with the equation. I'm going to plug in 4.19 is equal to the negative log of 1.8 times 10 to the negative fifth. But what I'm going to do, I'm just going to solve for that ratio, and then I can tweak the concentration of each individual part of the ratio. So go ahead and tell me what you guys get for the ratio here. Okay, when you solve for x appropriately, you get x is equal to 0.279. Well, how does that help me? What is this the ratio of again? What over what? The ion over the acid. So how can I translate that to make it useful? This is the same as saying 0.279 to 1, right? So I could keep it like that and say, okay, I need 0.279 moles per liter of sodium acetate, and then I need 1 mole per liter of acetic acid. That's acceptable. If that's not enough for you and you like to make things difficult, you could multiply both by 2 or by 4, whatever. As long as that ratio of acid-base concentration comes out to be 0.279, you've got the appropriate concentrations. So if I were in a hospital, I was a pharmacist, I knew I needed to make a solution of a particular pH, a buffer solution. I could figure out what I needed to mix when, even though I don't think pharmacists actually do that. But one thing I can say is every time I have been in a hospital with one of my parents, as you get older, your parents are sick a lot. So I've spent many an hour in hospitals, and every time one of the surgeons find out I'm a teacher, a chemistry teacher, they always bring up Henderson-Hasselbalch. It's the weirdest thing. First they start with like, oh, what is AU? I'm like, really? Can you make it a little bit more challenging? I'm saying that's like me asking you how many chambers of the heart there are. Come on, step it up a little bit. And then they're like, oh, okay. And the only equation they remember is Henderson-Hasselbalch. It's really kind of funny. And then oh yeah, no problem. And I spit it out, and it's funny. Good times. You never know when your chemistry knowledge is going to come into play in your life. Stupid party tricks. Okay, now that I've bored y'all, let's move on. Given a solution of ammonium chloride, what additional reagent or reagents are needed to prepare a buffer from ammonium chloride? What else do we need if we have ammonium chloride? What is ammonium chloride? That's ammonium chloride. So what do we need? Good. We need ammonia as well. Okay, so those are our two parts. This is really NH4+. Explain how this buffer resists a change in pH when A, moderate amounts of strong acid are added. The reason they say moderate is any buffer can be annihilated. If you add enough strong stuff to a buffer, it's going to use up all the conjugate or use up all the weak acid or base, and it can be overwhelmed. So that's why they use the word moderate. So if we add acid, how are we going to take the acid hit here? What is that going to react with in this particular buffer system? Good. And we're going to make our conjugate. So by taking a strong acid and turning it into a weak acid, we help stabilize the pH. B, moderate amounts of strong base are added to the buffer system. What's that going to react with? I know this seems simplistic and I keep saying it over and over again, but it's going to be helpful, so just bear with me. Plus water. And again, we turned a strong base into a weak base, helping to stabilize pH. Now let me ask you this. How is the pH going to be affected if we take the buffer and we dilute it? We just pour a gallon of water in the buffer. Is the pH going to change? How is it going to be affected? pH is equal to the negative log of the K. I want you to focus on this part. Focus on that. Will the pH change? All right, Catherine McGee said it correctly. As we add water to this buffer, we're going to keep this ratio the same. In other words, we're going to dilute this and this equally. So the concentration of each might change, but they change proportionally. So the same ratio leads to the same pH. Okay? That's asked a lot. They'll try to trick you a lot about adding this water business. Oh, it's going to dilute it and make it more toward neutral. I don't know what people think, but it's not going to change that ratio, okay? All right, oh, number 17. Guess what that is? It's called an invader problem. Let's go ahead and talk about invaders. So go back to the page that has this on it. We're going to do the simple invaders today just to get your feet wet, and then I'll start with the hardcore invasions on Monday, okay? Invader problems. How these are going to be different than any other problem you're ever going to see is that you're adding something strong. And what do I mean by something strong? You're adding an H plus or an OH minus to anything we've studied so far. We're adding it to a solution. That could either be a weak acid base, a salt, or a buffer. So here's my scenario. This is when I go crazy with the metaphors. Our solution that we're starting with is an equilibrium, happy, hanging out. It's like a little planet out in the universe doing its own thing. Then the space invaders come in. Space invaders are very strong, and there's two kinds of space invaders. There's the H pluses and the OH minuses, and they're going to invade. When they invade, little happy people on planet weak salt buffer planet there want to fight. There's going to be a fight. After that fight, we'll have to see who wins. Sometimes the invaders win, sometimes the solution wins, but we have to determine that. And from there, with whatever the, what's it called after war, the people left over, not survivors, there's a word. There's a different, well, not casualties, but the what? Collateral damage, no. It'll come to me in a minute. Anyway, these survivors are going to determine what the pH is. The hardest part about this is the war and figuring out what's left over, figuring out the collateral damage and figuring out what's left over after the war. So our war is this part. And to do our war, we're going to use, it's similar to a rice table, but I call it a stoic table, because instead of concentration, we put moles in it. Okay? And I'll teach you the stoic table here. It's going to be easy for you. It's going to be super easy. All right, so let's go ahead and let me just introduce how to do a problem. Go back to that number 17. First thing to realize is that this, see that it is an invader. How do I know it's an invader? I'm mixing something strong into something we've already talked about. Do you see how I'm mixing this H plus into a buffer system, right? So right there, you know, poor little buffer land is getting invaded. So we have to indicate through an equation for a stoic table what the invasion is. This is one of the hardest parts, is writing your initial equation. So let's talk about our happy-go-lucky world out there. What does our happy world of the buffer system have in it? Read the problem. Acetic acid, and what else? Okay, so you're getting to the point now where I'm hoping you're seeing that these spectators, we don't even write them down. So that's our happy world, correct? The invader, in his spaceship, is going to go in and invade the world. I worked really hard on that. It's like the Jetsons. Okay. When we write our first equation for our stoic table, you always start with the invader because it's the invader that's going into the system. Now, which one of those parts is the invader going to react with? The AC minus, and there's an end to the war. It's a single-headed arrow. This war is going to be done. So a single-headed arrow, and what is it going to make? Look up here. What is it going to make? HAC. Oh, isn't that weird how it made the other part of the little world, right? Didn't that work out snazzy? Okay, now we start our stoic table. What you're going to do is you're going to put in initial moles of everything in the actual given problem. So you're going to get really, really fast at this. To find moles, you always are going to take the molarity times the liters. There are a lot of people out there who work in millimoles and choose to not convert that mils to liters and just find millimoles. I don't like that. I'd rather just multiply molarity, the 0.525 times the 0.125 to get moles. So let's go ahead and do that. For H plus, 0.525 times 0.125 is what? 0.0656? All right, so remember, that's moles. What's our initial moles of AC minus? We have 1 mole of sodium acetate at 125 mils of it, so it's 0.125, and then this one is 0.125. Everyone see that? 1 molar times that. Okay? All right, so this is the war, folks. We got our battle going on. We're going to treat this just like a rice table. It's a one-to-one-to-one relationship. Which one of these is going to run out first? The invader minus 0.0. Because it's stoichiometry 1-to-1-to-1, we're going to treat it like the x, 0.0656. And here we gain the 0.0656. These are moles. Look, the invader's gone. The invader did not win. Our people won. Yay! The invader lost. So what do we have here after the AC minus? When we subtract, we get 0.0594. And remember, this is moles. And then here with AC minus, we have 0.191 moles. Yay, the war's over. That's awesome. So now we have to find the pH. The war is over. What do we have floating around? Don't worry about this left and right, who's on right, who's left. These are free-floating species in the beaker. We have a conjugate left over, and an acid. What do we have left over? A buffer system. Now it's a problem. It's number 4 here. You already know how to solve it. But be careful. You can't use Henderson-Hasselbalch because it's in moles. So what do we need to convert that to? Molarity. So we're going to divide both of these, be careful, by total volume. So that's 125 plus 125 because we mix those two things together. And we get 0.250. So what is our concentration of AC minus? 0.238. And what is our concentration of HAC? 0.763 moles per liter. All right, so now I've got my two concentrations to solve. I'm just going to plug it into Henderson-Hasselbalch. pH is equal to, and again, the Ka of acetic acid is 1.8 times 10 to the negative fifth, plus the log, which goes on top. Tell me the number. What number goes on top? Good. 0.238 divided by 0.763. So pH is equal to 4.24. That's what last period got. Would y'all get? Yes. Yeah. Okay, so what other scenarios would we have? This is a scenario where we have left over the acid and the conjugate base. Okay? What happens in my little world if all I have left over were this acid? What would I do? I just have an acid. What do you do when you have a weak acid left over, or a weak acid period? Take the acid, add it to water, put it into a rice table, and solve for pH. You have to be in molarity there. So you have to convert this to molarity in that case. What happens if I have just this one left over, just that guy, which is not the order it would be in, but there are situations where you only have the conjugate left over. What type of scenario is that? Louder, Stephanie. Hydrolysis. That's the conjugate of in a salt. Okay, so you take that, take its molarity, convert it to molarity, put it in a rice table by adding it to water. What else do you have to do in a hydrolysis problem? Convert the K by using kW. That still stands because remember, after the war, you know, that's all you have left in the system. So you just start from scratch there when it comes to finding the pH. Now here's the kicker. If you have strong left over, 90% of the time, you're going to have something else left over with it, like you'll have strong and a conjugate or something. If you have strong left over, strong wins the battle. So you don't even have to consider the contributing moles from the other species because the strong is going to be so much stronger. These are mathematically negligible. So if you have strong left over in combination with whatever, you just go to the strong moles, convert to molarity, and then take the negative log of it. That's all you have to do. So strong being left over, even though we don't like the Invader, is actually the easiest one to solve because you just go negative log of those moles. Okay, let's do another one. We're going to do two more. 125 ml of 0.5 molar sodium hydroxide is added to a weak acid. We're adding an Invader to number 2 on the board. So first step is to start the war by writing an equation. This is an easy equation. We always start with the Invader. What's our Invader? OH minus. And who's he attacking? The world of acetic acid. The war is going to have an ending, so it's a single-headed arrow. What are we going to make? Water and AC minus. Okay, since this is a stoic table, we have to be in moles. Got to be in moles to figure out who's going to be left over at the end of the war. So to find moles of the, starting with the sodium hydroxide, 0.125 times 0.5 is 0.0625. And then HAC, we've got 0.15 times. Same thing, right? So we get 0.625. 0, and who cares about water? So it looks to me like we're going to lose the same amount here. We get minus 0.625 moles of this, minus 0.0625 moles of that, plus 0.0625 moles of that. So we're out. But here we have 0.0625. Here's our only survivor of the war, this guy. So now the war's over. That guy now has to live on and be a pH. So what do we have to do? Not yet. got to convert to molarity. To put it in a rice table, we have to convert to molarity. So we're going to divide by a total volume of 0.250, and it's going to give me a molarity of, the acetate ion is going to have a molarity of 0.250 moles per liter. Now I heard someone say earlier, take it, add it to water, and we're going to put it in a rice table. So we're done with this problem. Don't look up here anymore. Finished. Just look at that molarity. So we're going to have the acetate. We're going to add it to water, and we're going to get AC minus plus, not AC minus. How about HAC plus? Plus OH minus. One thing which would have been given to you in most problems is your K, not most problems, in all problems. So we're going to have an original concentration of 0.250. And this is all old hat to you guys now. Where did that saying come from, old hat? Do you ever wonder? Minus. You haven't heard this is old hat? Okay, after this lecture, we're looking this up because I did not make that up. You guys are just too young. All right. Minus x plus x plus x. We can trumpet. So since we're trumpeting it, we get, x squared over 0.250. Remember, that x is an OH, so we need a KB. Well, we only have a KA. So to get KB, we get 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. So just keep solving and solve for x, and someone tell me what x is, which is equal to the OH concentration. So 1.2, 1.17 times 10 to the negative 5th. So that's my OH. So can someone tell me my POH? Oh, there goes the smart board again. POH equals 4.93, and a pH is therefore 9.07. The smart board's still blinking. It'll hopefully get back someday. pH 9.8. All right. Okay, I'm going to turn the video off in preparation for this next problem. I want you guys to set it up and go as far as you can. Those at home, I want you to pause this video now and try to set this up on your own. And when you restart it, it will have the answer all written out for you. All right, here's the answer. Let me talk you through it real quick. We start out, we're invading acetic acid world with an OH, so we make the acetate ion and the water. Our original number of moles of sodium hydroxide is 0.5 times 0.2. That gives us 0.1. Our initial moles of the acetate is, the acetic acid, excuse me, is 0.5 times 0.125. So when we do the subtraction, we're losing 0.0625. We end up having 0.0375 moles of the hydroxide and 0.0625 moles of the acetate. But because there's something strong left over, strong wins. So we're going to convert those moles to liters by dividing by 0.325, which is the sum of 200 plus 125 mils. Divide by that liters, and we get our OH concentration being this, negative log 14 minus that. And that is the world of the simple invaders. Okay, so it's so important. It might seem easy that I did it with you, but I need you, no excuses. I don't care if you have 102 average in this class and have never done homework before. I want you to work through some of the homework problems to make sure that when you're by yourself, it doesn't get all jumbled up in your head, because it so easily can.